Here's the screencast on electron configuration. So let's review what we learned last time. So here's the nucleus, and electrons are in energy levels surrounding the nucleus. You can't change what's in the nucleus, but we're just really talking about the electrons. So in the first energy level, there is an s orbital, so to speak, and the s can hold 2 electrons, and you draw one going up and one going down. You could do it as a crisscross if it made you happy, 1 and a 2. And then as we move away from the nucleus, it takes a little more energy to go away from the nucleus. We go to the second energy level out here. And the first place an electron would go is S, and then the second one would go there. And then we move to the P's. So the second level has 2 things. It has S's and P's. And if the P's filled up, they would go there, there, and there. It's called Hund's rule. It's the crowded bus rule. Each electron wants to take its own bus seat and be as far away as another electron as possible. And then the 4th one, the 5th one, and the 6th one come in. So the P can hold 6 electrons, but again, they fill it up individually before they pair up. Now, what's important is I might ask you how many unpaired, we have to fill this one up if those other ones are filled up, how many unpaired electrons does this atom have? And you would say 2, because there's one that doesn't have a pair, and there's another one that doesn't have a pair. So let's say we move to the 3rd energy level. And again, this S would be filled, and then you fill the P's, and then after the P's you get the D's, and you'd fill the D's, and then you go back and double them up. It's just easier for me to click on these at this point in time. And then if you were to move out to the 4th level, you do the S's, and then you do the P's, and then you do the D's, and then what gets added are the F's. And notice these go up by odd numbers, so there's 1 of those, 3 of those, 5 of those, 7 of those. So the max they can hold, S can hold 2, P can hold 6, D can hold 10, because each one holds 2, and there's 5 of them, 5 times 2, and F's can hold 17. And I know you might see these letters here, K, L, M, and N. They do deal with quantum mechanics, but we're not going to use them at all. So the shapes of the sublevels, or the orbitals. So the S sublevel is a sphere. It's convenient that S and sphere both have S. And it can hold a max of 2 electrons. If we move to the P, you could say peanut or dumbbell. It holds a max of 6 electrons. And what this really is that if you were to envision this as a graph with an X, Y, and Z axis, here is one peanut, and it is going along the x-axis, so it's called 2px. Now this one switches, and it's along the y-axis, so it's called 2py. And this one then is along the z-axis, and it's called 2pz. So you can have 2 electrons there, 2 there, and 2 there. But again, they don't fill it up 2 at a time. They go 1, 1, 1. Then they double up the other, the other, the other. Now the D is cloverleaf. It looks a little bit like a cloverleaf or a donut, because that one looks like a donut with its jelly squirting out. It holds a maximum of 10 electrons because you have 5 of them. 1, 2, 3, 4, 5, which can each hold 2. 5 times 2 is 10. And again, they fill it up 1 at a time. They'd go 1, 2, 3, 4, 5. And then 6, 7, 8, 9, 10. And these are even more crazy. You can see that their designations down there are crazy mathematical formulas, and there's no need to know those. And if we get to the F, F kind of stands for flower, not so much really, but it holds a maximum of 14. So there's 7 of these different freaky shapes, F for freaky, and each one holds 2, so that's 14. So rules to know. Aufbau is German for Aufbau, is German for building up. Electrons fill up an atom one by one. They enter the energy levels in order from 1 to 7, relatively speaking. And note that there is some overlap of energy levels. We'll see this on a diagram. Some fill up before the others. For example, 4s actually fills up before 3d, even though the number 4 is bigger than 3. This is why chemistry is a little bit hard. So Aufbau means building up, and you build up from close to the nucleus to far away from the nucleus. So envision that this is the nucleus down here, and electrons fill from down here to up there, so from close to the nucleus to far away from the nucleus. And so the first electron would come in here, which is the 1s, and then the second one would go in there. And then the 3rd electron would come here, and the 4th one. And then it would move to the 2p. It's a little more energy, but we have them lined up here in the p's. And this is Hund's rule, the crowded bus rule. again, they fill up individually and then they would double up. So the most correct way to draw these is with boxes and these half arrows, but you don't have to. I'll understand it if you use little crisscrosses or X's. So then it would go to 3s, and then it would go to the 3p's, and then you would think it goes to the 3Ds, but if you look here, the 4s, what a lovely line, is a little bit lower than the 3D, so it actually fills up next. So then it would be 4s, and then it would be, I'm just going to wickle-wackle the Ds, the 3Ds, and then 4p. So how do you remember this? Because this is crazy. I remember it because I look at the periodic table and figure it out. But I will give you this upside-down squiggly chart of happiness. And this is how it fills. It goes to 1s. Let's do this in highlighter mode. So it does 1s, and then it snakes back down. It does 2s, and then it does the 2p and the 3s, 3p, 4s. Then you snake back down, and it does 3d, 4p, 5s. And you just keep following these arrows because we wouldn't actually go out that far. But just keep following them, and that'll give you the order of filling. And again, all the the s's here would hold a maximum of 2. The p's hold a max of 6. The d's hold a max of 10. I just wanted to write 5. 10, and the F's hold a maximum of 14, because we're not going to get to those other ones, which means S has 1 circle, P has, look at those three boxes, 3 circles, D has 5. Oh my gosh, I am winning some award somewhere. And the F then has 7 of those. I have repeated myself again and again. So 2 more rules. I've talked about this one already. Friedrich Hund, his rule is I call it the crowded bus rule. Electrons must be placed one at a time into individual orbitals before they are doubled up. Thank you, Mr. Hund. And the second rule to know is the Pauli exclusion principle. No more than 2 electrons are allowed in each orbital, and they must have opposite spins, and that's why they're drawn in opposite directions. He was the first to recognize the neutrino. That doesn't matter to us. Let's keep moving. So electron configurations. So where we're going with that filling up is electron configurations. And if you notice on your periodic table, there's already some beautiful stuff on there. So that's S1. Everything underneath there is an S1. Everything underneath here is an S2. And then after S, because it goes Seattle Police, these are the P's. P1, 2, 3, 4, 5, and a 6. So everything underneath there is P6. And then you see P1, 2, 3, 4, 5, and then 6. And then so it goes Seattle Police Department. Then we have the D's in here. And then last but not least, we have the flatulence, or the F, here out the bottom. So there really are blocks of the periodic table, which is quite handy. So this is the S block. This is the P block, except for helium. I shouldn't have put helium in there. This is the D block, and what color do you think flatulence is? Probably brown. I don't know. And that's the F block. So how do these electrons fill up? What we're really trying to get to is, they're called electron configurations. So how are electrons configured in each element? And each element has its own configuration because it's like a house on a street. It's the only house on that street on the whole planet. And we use this, I call it the upside down squiggly chart. Some people flip it and do it the other way, but I love my upside down squiggly chart because it represents filling from the bottom outwards, from close to the nucleus to further out. So an electron configuration has this kind of notation. And you'll see a 1. 1 represents the energy level. S represents the sublevel, so you could have sublevels S, P, D, or F. And the superscript of a 2 represents how many electrons. So let's see if we can do some of these. So if I were to ask you, what is a configuration of an element that has 4 electrons? So you really just go to your squiggly chart, and you first fill up the 1s. So there's the 1s, and you put in 2 electrons into it. And then you move up to the 2s, and you write 2 and then s, and then you put 2 electrons in it, and you add your superscripts to see if you're at 4 electrons yet. And 2 plus 2 is 4, so we've reached 4 electrons. So these are all neutral. 4 electrons would mean it has 4 protons, so I might ask you, what element is that? So you find element number 4, 1, 2, 3, 4, it's beryllium. So let's try another one. This one is an element with 9 electrons. So we go to the 1s and we fill it up 1s2, and then we move to the 2s. So 2s, the s can hold a maximum of 2. Then we move to the 2p because that's the next on our line, and we write 2p. And we got to add up to 9. So we have 2 plus 2 is 4. And to get to 9, it would be 5 more. P can have a max of 6, so we can have a 5. So you would, this element's electron configuration is pronounced as 1s2, 2s2, 2p5. And what element is number 9? Number 9 is element, I can't quite read on that screen there, is fluorine. Oh, fluorine's a wicked element. So let's try manganese, which is number 25. I think we might need to move this chart a wee bit. Okay, so manganese is number 25. So we just start out with 1s2. There we got it. Then we do the 2s2. And then we do 2p is next. 2p will fill that all the way up because that's a 6. Then we go to 3s. We'll fill that up with a max of 2. And are we there yet? 2 plus 2 is 4, plus 6 is 10. So we're at 12. We're not quite there yet. And then we do a 3p. 3p, fill it up with 6. After 3p comes 4s. So 4s superscript 2. We're almost there, not quite. Now we drop back down and we pick up the 3Ds, so 3D, and this all adds up to 20, and we just need 5 more to get to 25, so the D will hold 5 electrons. D can hold a max of 10, but it definitely can hold 5, 3D5. So that is the configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. And Miss A actually has a little shortcut. I say manganese. Where is my friend manganese? There it is. And let's make this a little bit bigger. Maybe it'll help us. I find my friend manganese because it's for men. And I find what the end of it must be. And do you see this little 3D there? So it ends at 3D5. And so I go back to my little squiggly chart of science. And I say, aha, I am starting at 1s and I'm ending at 3D, so I'll just write all those and fill them all the way up until I get to 3D, and 3D will be 5. So Miss A has a little shortcut. I always find out where I'm ending, and then I just go from the beginning to that ending point or spot. So again, the electron configuration, the number in front is the energy level, the letter is a sublevel, and the superscript is the number of electrons. I think we did it all. Let's do some orbital diagrams because I'll ask you to do orbital diagrams. So these are using arrows, and it's using the number and the letter, but then we don't use the superscript. We use lines or arrows or crosses to represent that. So let's practice this for hydrogen. So you would write 1s, and then you would write either a box or a circle or a line. So hydrogen is a 1s1, and so technically it's just a half of an arrow. If you wanted to do the circle, you could still do a half of an arrow in there. Or if you wanted to do just the flat line, it would be half of an arrow. Or you could be a little bit lazy. I find the circle the easiest one to draw. You could just do half of an X. So if we move to helium, helium has, there it is, it's a 1s2. And so I would probably draw the flat line, and you draw 2 electrons. You could draw it like that. You could draw it, look at that lovely tiny circle, like an X. Boy, I really speared my circle. And then if we moved on to lithium, lithium has a 1s. I'm going to draw a flat line here, and 2s, they just represent 1, and the s is filled, so I'll put an X there, or you could do the arrows, and then the 2s, it ends in a S1, so it just has that. And if we were to do oxygen way over here, oxygen ends in a P4. So the 1s is filled up, crisscross my applesauce. 2s is filled up. Now the P, I'll draw it in here. 1, we need a new color, peoples, so you can see it. 1. So P has 3 orbitals, so you have to draw out 3 lines or 3 boxes or 3 circles. And we are filling it up to 4. This is where Hutton's rule comes into play. So 1, 2, 3, and then we pair up. Because what I might ask you is how many unpaired electrons out there? There's 1, 2 unpaired electrons. So oxygen must have something special going on. In fact, I'll give you a little hint here. Since oxygen is missing that one and that electron, it gains it from another element to become that 2- that we've talked about in the past. So let's do some practice. Write the electron configuration for magnesium. So there's magnesium. Magnesium ends in an S2, so I would look at my chart and I would go 1s2, and I keep going until I get to actually the 3s2. 2s2, then after 2s2 comes 2p6, and then after the 2p6 comes 3s, and it looks like it ends in a 2. All of those superscripts should add up to its element number, which is 12. So 2 plus 2 is 4, plus 6 is 10, and then that makes 12. So I might ask you, what element is this? This next question, you just add up the superscripts. So 2 plus 2 plus 6 is 10, 11, 12, 13, 14, 15. It must be element number 15, which is phosphorus. And you could also do it a different way. You could take a shortcut. I like to look at this end part. It's kind of your key to the whole thing. So you find row 3, so here's row 3, and you go way over to the P3, and that leads you with element P, phosphorus. That's how I do it. I don't add up those superscripts. This next one says, write an orbital diagram for fluorine using half arrows. Okay, so my friend fluorine. So fluorine is here. It ends in a 2p5. So we're going to have a 1s with a line, and it's going to be filled. And we don't write them as superscripts on this one. We're going to have a 2s with a line, because s just has one line. And then after 2s comes 2p. And we're going to have 1, 2, 3 lines, and it is filled up to 5. So 1, 2, 3, 4, 5. So P has one unpaired electron. I mean, fluorine does. So that's what we were just talking about, was the unpaired electrons. And next time we'll do the exceptions. Until next time, ciao.